Okay, so we are going to look at something called Euler Buckling. So let's just draw a diagram. So if we say we have a beam that is supported like this, it has a length of L, and it has a load P there. P. So we know that both ends, they are pinned. The lower uh, uh, the lower end cannot move. Lower end cannot move, and the upper can only move in the direction of the beam. The upper can only move in the direction of the beam. We also know that the member is perfectly straight and the load P is concentric. So the member is perfectly straight. And the load P is concentric. Is concentric. Also for this case, we know that Hooke's law is valid. Hooke's law is valid. Okay. In addition, we know that the deformation is small. So hence the curvature of the column can be approximated with the second derivative of the deflection. The curvature of the column can be approximated with the second derivative with respect to x squared. Okay. So let's just take a small cut of this beam and look at what's going on inside that cut. So if we have, because this will buckle, it will buckle out like this, and this is kind of where x is. This is the cut, and this is the y-axis, and we have the force P there. So this distance will be y. We also know that this P will also be internal in the beam. And we have a moment here, m of x. Now, if we take the moment about this, about A, let's call this part A. We know that the sum of the moment about A, and if this is the positive direction, this should be equal to 0. This is the moment. So we know that we have this moment, it's positive, minus, well, we have the force P times the distance y. It goes in the negative direction. Minus Py. So m of x. And this should be equal to 0. Okay. If we solve for the moment, we get that the moment m of x is equal to Py. And we know that y is in terms of x, so we get that the moment, the function of the moment, is equal to Py of x. And we can use the curvature equation. It says that ei y prime prime is equal to minus m of x. Then this should be equal to ei y prime prime is equal to minus Py of x. And because y prime prime is also a function of x, we can just say that this becomes then ei y prime prime plus Py equals x. So this is a function of x, and this is a function of x. So we keep all of the x's on one side. So then we have the governing equation is therefore ei y prime prime plus Py equal to 0. Okay. If we now let P divided by EI, so let P divided by EI equal to K squared, we see that we have y prime prime plus K squared y equals to 0. You recognize this as a second order ordinary differential equation. This is the second order differential equation. Okay, the solution to this is given by the characteristic equation. Characteristic equation. This is given by lambda square plus k square equal to 0. If we solve this in terms of lambda, we get that lambda is equal to the square root of minus k squared, which gives us lambda 1 and 2 equal to plus minus ik. All this should be familiar from calculus 1 and 2. And we know that this gives a general solution of y of x is equal to, because we have a complex lambda, we have the complex solution a cosine kx plus b sine kx. So a and b are arbitrary constants. And we can choose these constants by using the boundary conditions. Using boundary conditions. Okay. So if you remember that our figure here, we see that y of 0 should be equal to 0 and y of L should be equal to 0. So if we use the boundary conditions and y at L equals to 0, we get that y of 0, so 0 should be equal to a cosine a times 0 plus b sine a times 0. This is 0, so that means that a cosine of 0 should be equal to 0. And since this part is equal to 1, that means that a must be equal to 0. If we use the other boundary conditions, y of L equal to 0, we get that b sinus k L, this should be equal to 0. And since we don't want b to be equal to 0, so the solution here is actually b can be equal to 0 or sinus to kl to be equal to 0. This part is the trivial solution. Everything can be 0, of course, but this is not interesting to us. So let's say that sinus kl is equal to 0. So if sinus kl equals 0, we know that if we take the inverse or arc sine on both sides, we get that kl will be equal to sinus inverse of 0. And this is equal to n times pi. So every multiple of pi, where n is equal to 1, 2, 3, and so on, this is valid. So that means that the kl is therefore equal to n pi. Now if we square both sides, we get that k squared L squared is equal to n squared pi squared. And we solve this for k squared. N squared pi squared over L squared. We can substitute back that k squared is equal to p over ei. So p over ei is therefore equal to n squared pi squared over L squared. And solve this with respect to p. We get that p is equal to n squared pi squared ei over L squared. Okay. So what we actually see here that we have a critical load. So the critical load P is then equal to n squared pi squared ei over L squared for n equals 1, 2, 3, and so on. So our function y of x equals then b sinus of n pi x over L for n equals 1, 2, 3, and so on. Now that b is an indeterminate, which means that the direction and magnitude of the buckling shape cannot be determined. It's undetermined. So pinned end column, it will buckle at n equals 1. And this case is the fundamental case of column buckling. This case is called the fundamental case of column buckling. Therefore, the critical load PCR is therefore equal to pi squared ei over L squared. The shape function of buckling is given by y of x equals b sine pi x over L. In the next video, we will go over an example.